So here we are. Actually, this is really interesting and very, very different. We're going to talk about how the leading term, the highest degree term in a polynomial, can tell you a lot of information that actually could make your work easier. So let's look at this. We have f of x equals x to the 7th power minus x to the 3rd power plus 6. The highest degree term, the highest power term, is this, x to the 7th. That's the leading term. And the power of the leading term is 7. The exponent is 7. So the degree of the entire polynomial is 7. Now, so what? Here's what, so what? That 7 tells us the maximum number of real zeros that this polynomial can have. 7. That's the most zeros it can have, and therefore it's the most x-intercepts it can have. Does that mean it has to have all 7? No. Could have 6, could have 5, could have 4, could have 1. But it will have at most 7. Now, on the other hand, what about the turning points, the relative maxima and minima? Those will always be 1 less than the degree of the polynomial. So 7 minus 1 equals 6. The maximum number, the most turning points that this can have, that is the most relative maxima or minima, is 6. Or it can have less, but the most it can have is 6. Same thing here. Here, the leading term is 7x to the 4th. The exponent of the leading term is 4. So the degree of the entire polynomial is 4. So 4 is the most, the maximum number of real zeros. And since real zeros make x-intercepts, that would be the most x-intercepts it can have. And the maximum number of turning points will be 1 less than 4, which is 3. It can have less than those, but not more. And here, the highest power, the highest power is 3. The leading term is x to the 3rd. Therefore, the degree of the entire polynomial is 3, which means that the degree of the polynomial is 3. The maximum number of real zeros f of x can have is 3. The maximum number of x-intercepts is 3. And the maximum number of turning points is 1 less than 3, which is 2. Simple pimple. This could not be easier. Just takes a little bit of memorizing. Okay. Making sure I really did record. Now, before we do this, I want to go on to something else that's really, really easy. Okay. Suppose a polynomial of degree 4 with rational coefficients. Those are the coefficients that we would call normal coefficients. Numbers like an example might be f of x equals 3x to the fourth minus 5x to the third. I'm just making these numbers up, plus 2x squared plus x minus 5. Okay, the coefficients are the numbers in front of the x's. That's an invisible 1. These are what we would think of as being normal kind of numbers. They're real and they're rational. These are real and rational coefficients. So when this says you've got a polynomial of degree 4 with rational coefficients, they don't even have to bother to say real, then what we have to do is look at the zeros they give us. This is a rational 0. And this is a rational 0. I mean, it's just a fraction, but there's nothing special about it. It's just a kind of a normal number. We like them because you can always find the exact answer. This, on the other hand, is not a rational number. It can never be expressed exactly as a fraction. This is called an irrational 0. We've been through this before. Now it matters a lot. When you know that your polynomial is going to have rational coefficients, which are real, they have to be real, otherwise rational doesn't matter. Okay, so read real and rational as normal kinds of numbers that you're used to. When there's an irrational number that's a 0, it's got to be true, if you're going to have normal kinds of numbers, that its conjugate also has to be there. So since the square root of 2 is a 0 of the polynomial they're talking about, then its conjugate, negative the square root of 2, has also got to be there. And so the answer to this problem, there's no more work that you have to do. All you have to do is type this into the answer box. Negative the square root of 2. That's all they're asking. If these are zeros, name the other zeros. Well, there's only one other. Negative the square root of 2. Let's look at this. Here you've got a polynomial of degree 4. These are what are called the given zeros. That is, they're given to you. There's a 0, we'll call it Z1. There's a 0 that equals negative I. So for there to be rational coefficients, normal kinds of numbers like this, on the polynomial that we're going to build, for there to be rational coefficients, this complex number has got to be accompanied by its conjugate. And this irrational number, 4 minus the square root of 7, has got to be accompanied by its conjugate, 4 plus the square root of 7. So the answer you would put in the answer box would be that the other zeros are negative I, positive I. This is negative I. Its conjugate is positive I. Okay then, the other zeros, these are the other zeros. If negative I is there, right there, then positive I has got to be there. If 4 minus the square root of 7 is there, then 4 plus the square root of 7 has got to be there. There's Cattail. George is in the house. Big old George. Say hi. Say hi to everybody. Hi. Yeah. There you are. You're my pal, aren't you? When you're good, you're my pal. He's not good all that often. Oh, yes, you are. I and 4 plus the square root of 7. These are the other zeros. If you want to have rational coefficients, real and rational, they're leaving off real, and I'm not sure why. Okay, I think they're saying to themselves, well, if it's rational, it's real. The rational numbers are in the real numbers, but students don't always know that. So you need to know that when you see rational coefficients, you need to think real in the real number system, and rational can always be expressed exactly as a fraction. Real and rational coefficients, that's what you need to think to yourself. And coefficients are the numbers in front of the letters, in front of the variables, in a polynomial like this. Okay, now, there are just a couple of more. I just want you to get the idea of this. Suppose you have a polynomial of degree 4 with rational coefficients. Well, here are the zeros you're given. What is the other zero? This is rational, real and rational. This is real and rational. This is complex. A complex zero is going to be accompanied by its conjugate. So your other zero in the answer box is going to be the conjugate of positive 8i, and that's going to be negative 8i. So that's what you would type in the answer box. And then finally, suppose you have a polynomial function of degree 4 with rational, think real and rational, coefficients. Well, let's look at what we're given. We're given 4 plus 2i and 5 plus the square root of 5. Okay, 4 plus 2i is complex. It's in the complex, not in the real number system. And 5 plus the square root of 5 is in the real number system, but it's irrational. if we're going to have real and rational coefficients in front of all our variables in this fourth degree polynomial, the only way that's going to happen is if 4 plus 2i is accompanied by its conjugate 4 minus 2i, and 5 plus the square root of 5 is accompanied by its conjugate 5 minus the square root of 5. So these are going to be what you put in the answer box because they're just asking about, hey, what are the other zeros? And you have to know they're going to be there. The other zeros. And that's what you put in the answer box for this problem. So the first set of problems and the last set, we were on the last set, here's the first set. All of these are incredibly easy, and for people who got here later, all it tells you is that if you have this polynomial and the leading term is x to the 7th, then the degree of the polynomial is 7. You're going to have at most that many real zeros. You could have less, but not more. And at most 7 x-intercepts. And at most 7 minus 1, which is 6, turning points. The number of turning points, that is the maximum number of turning points, will always be 1 less than the highest power of the polynomial. Now, we're going to get down to the heart of it now. But at least 2 of these 3 very short homework sets. The second one, the middle one, is more challenging because you're going to learn something that's new and that you really have to think about and memorize. And that's this. All this time we've been saying that the only way to factor a polynomial is if it's factorable. Okay? Is it factorable? Can you use the AC method on it? Can you use the short grouping method on it? Can you use the difference of 2 squares on it? Can you use any of the other GCF? Any of the factoring methods you used? If not, then it's not factorable. But that's a lie. Just thought you'd like to know. The truth is, all polynomials are factorable. And we're getting into, well, what happens? What happens if you can't factor them? Well, that's the hard stuff that we're getting into now. We have this formula that can be used with polynomials. Here, because we were given 3 zeros of this function of degree 3, I only made room for 3 zeros there. But this is the formula you use to take zeros, put them into factors, and then multiply the factors together to get the polynomial. So here's the secret of the universe, right here. The zeros of functions. Let's say the zeros of polynomials build the polynomials. They're the seeds that grow up and they give birth to the polynomial function itself. It all starts with these three numbers for the problem we're going to do now. So the zeros of polynomials actually build, they create the polynomial. And they do that in the following way. You list your zeros like this. Z1 equals -1. Z2 equals 2. Z3 equals -7. Now A is going to be the leading coefficient of the polynomial. We're not told what it is here, so we're going to assume it's 1. Now I'm going to use the factor formula to put this together so that I can find the polynomial that these three zeros build. Okay, so x is going to equal 1 times x minus z1 times x minus z2 times x minus z3. Now I'm going to clean it up a little bit. Minus minus is plus, so this will be x plus 1, x minus 2, x plus 7. Remember that when 1 is multiplied by anything, it disappears. So this is what we're going to multiply together. The way I do it is I multiply the last two terms together first. It's not a rule. I just found it easier. You can find your own way. Okay, when I multiply these together, I'll have x squared plus 7x minus 2x minus 14. So f of x will equal x plus 1 times x squared plus 5x minus 14. Now, I've got x plus 1 Okay, now watch this. I am going to do the following. So that's why I skipped a place so you could see clearly. I've got x plus 1. I don't even need to do it like this. I was going to kind of set it apart, but no, let's just be big kids here. I am going to take this x and multiply it by this set of parentheses. My dog just fell out of bed. Then I'm going to take the plus. I have such a great little household. I'm going to take the plus 1. So let me make. There's Ayla. She's walking in here. Are you okay, Ayla? Ayla? Yeah, she's walking around. I guess she's okay. I'm going to take this plus 1 and multiply it by, hello, baby. Hello, baby. It's okay. It's all right. Yeah. You have to reassure your children when they fall out of bed. Except the cat now is telling me not to pay attention to the dog. I wonder why. Okay, plus 1 times the second set of parentheses. The joy of working from home. My goodness, you never know what adventures you're going to run into. There. Okay, now, so here we go. Now we distribute. We take x and multiply by x squared, x and multiply by 5x, x and multiply by negative 14 or minus 14, and plus 1 and multiply by x squared, plus 1 multiply by plus 5x, plus 1 and multiply by minus 14. Here I go. This will be x to the third plus 5x squared minus 14x plus 1 times x squared plus 5x minus 14 is x squared plus 5x minus 14. Now I combine my like terms and I'll be done. X to the third is the only cubic term I have. Now I'll have 5x squared plus x squared. Oh, that went down way too low. There. Okay. Plus 5x squared plus 1x squared is 6x squared. Minus 14x plus 5x is minus, no, it's minus 9x. And minus 14. So that is the polynomial function that is built from the interaction of these three numbers. And that's how zeros create polynomials. That's the first one. That's the easiest one. Let me go back. Yeah, that is the first one. Okay, after this, they get harder. Because check out these real coefficients. No. You're making these zeros 2, 6i, and negative 6i, and these are conjugates. So I can make real coefficients that also incidentally will be rational. I'm going to use this formula with these 3 zeros. Again, I'm going to let A equal 1 because they haven't told us what A is. And that actually is the way it's supposed to be. They're trying to introduce you to multiplying the factors together before you have to include a number in front. Okay. So you're going to have x minus 2. Oh, I forgot to label the zeros. Z1 is 2. Z2 is 6i. Z3 is negative 6i. And these are conjugates, which is important here. It's the only way you can get real and rational coefficients. So we're going to say x minus 2 times x minus 6i times x minus negative 6i. And of course, you're going to negative times negative is positive, so this will be f of x equals x minus 2 times x minus 6i times x plus 6i. Okay, let's start multiplying. Now, there's a trick to doing this that will take you less time, so it's a very good trick. These are conjugates. I'm going to show you some other conjugates. There's a formula for multiplying conjugates, and here it is. So if you multiply these, you'll have a squared plus ab minus ab minus b squared. Now ab minus ab, boom, boom, bye-bye. So you'll have a squared minus b squared. Well, if you think of x as being a and 6i as being b, then you'll have a minus b times a plus b. And your answer then is going to be a squared minus b squared. So that'll be x squared minus parentheses 6i squared. You can only do that when you're multiplying conjugates. I love conjugates for that reason. Okay, So let's write it more neatly again. F of x equals x minus 2 times x squared minus 6i squared. Okay. Now, that's going to be x minus 2 times x squared minus 36. 6 squared is 36, and I squared is I squared. But I squared is something more. I squared, you remember, and if you don't, here it is. I squared equals -1. So x minus 2 times, oops, that's a square. Okay, x squared minus 36 times -1, which will be x minus 2 times x squared. Or minus 36 times -1 is plus 36. So now we're ready to go. We're almost done with this. We're going to have f of x equals x times x squared, x times 36 plus 36, minus 2 times x squared, minus 2 times plus 36. What this will give us is x to the third plus 36x minus 2x squared minus 72. So we're not quite done because we have to put this in the correct order, descending order. F of x equals x to the third minus 2x squared plus 36x minus 72. And there you have it. Okay. Now I know this part up here seemed really fast to you, so let me show you that you will get the same answer if you do this the long way. X minus 6i times x plus 6i. You can always do it like this. X squared plus 6i times x minus 6i times x minus 36i squared. So 6ix minus 6ix is 0. And you'll have x squared minus 36i squared, which is x squared minus 36 times -1, which is x squared plus 36. So it seems weird, but it's not. But you can only take this shortcut when you really, really, really have conjugates. Okay, let's go on. You'll get a feel for this after a while. Now, this one you're going to have to watch really carefully, and then you're going to have to watch the video really carefully. This one is going to be a toughie. Okay, again, we're letting A equal 1, so we don't have to deal with it. But Z1 is going to equal 2 plus the square root of 3. That's an irrational 0. This is its conjugate. Z2 equals 2 minus the square root of 3, which is also an irrational 0. And then 4. 4 is just a real rational 0. No, Z3 equals 4, which makes the poor guy just a little bit boring, but oh well. So f of x is going to equal, no, I'm going to need brackets here. And I'm going to need to write a little smaller. So this is going to be x minus 2 plus the square root of 3. I need to use parentheses around 2 plus the square root of 3 and 2 minus the square root of 3 because they're one number. Even though it's like a binomial, there are actually two parts to it. So times x minus 2 minus the square root of 3 times x minus 4. Now watch what we do now. Again, this is very important you follow these steps exactly, which is why you need to do problems like this over and over again using similar problems until you get it. Okay, I am going to multiply this negative sign, distribute the negative sign, which is multiplication, in here and in here, and this one in here and in here. And that'll give us x minus 2 minus the square root of 3 times x minus 2 plus negative times negative is positive. Times x minus 4. I'm not done. Okay, now. I'm going to group the x minus 2, and you'll see why. Okay, now I'm going to skip this step. I mean, not skip the step, but skip the line. For the following reason, I'm going to point something out to you. The x minus 2 and the x minus 2 are identical. So they are going to be A, and the square root of 3, they're the same. They're going to be B. And so I'm going to have A minus B times A plus B. And then I can't lose this guy. He's important. Okay, so now I'm going to multiply A minus B times A plus B, and that will give me A squared minus B squared. Times x minus 4. Okay, I'm going to get rid of that too, because this takes some notes. Notice that I have let A equal x minus 2 and B equal the square root of 3. So when I multiply A minus B times A plus B and I get A squared minus B squared, that means I'm going to have x minus 2 squared minus the square root of 3 squared. A squared minus B squared. So let's go back to our calculation now. And we're going to have f of x equals x minus 2 squared minus the square root of 3 squared times poor little x minus 4 that hasn't been used yet, but it will. F of x is going to equal x minus 2 times x minus 2 minus, now the square root of 3 squared is just 3, times x minus 4, who meanwhile has fallen asleep. So this is going to give us x squared minus 2x minus 2x plus 4. Oh, I don't need to write that big. My hand's getting tired. Oh, poor Miss Rademacher. X squared minus 2x minus 2x plus 4 minus 3 times x minus 4. And what that's going to give us is x squared minus 4x plus 4 minus 3 is 1. Oh, goodness, times x minus 4. We're almost done. The light is at the end of the tunnel. F of x equals, all right. I'm going to take x squared and multiply it by the second set of parentheses minus 4x multiplied by the second set of parentheses and plus 1 and multiply it by the second set of parentheses. So I will get x squared times x minus 4 minus 4x times x minus 4 plus 1 times x minus 4. And now it's just all calculation, normal kinds of calculation from here. X squared times x is x to the third. X squared times minus 4 is minus 4x squared. Minus 4x times x is minus 4x squared. Minus 4x times minus 4 is plus 16x. Now, plus 1 times x minus 4 is going to be plus x minus 4. So now all I have to do is combine like terms, which conveniently happen to be right next to each other. F of x equals x to the third minus 4x squared minus 4x squared is minus 8x squared plus 16x plus 1x is plus 17x minus 4. Oh, good grief. But notice all of these coefficients, 1, negative 8, 17, and negative 4, they are all real and rational numbers. Yay! Right. And that would not have happened if 2 plus the square root of 3 had not had its conjugate along 2 minus the square root of 3. A little strenuous. Okay. Wow, that took a lot out of me. But this, I believe, is the last one. And just like yesterday, we're going to be talking about multiplicity, but we're going to be talking about exactly what multiplicity means. So, find a polynomial function of degree 4. Okay, so the degree is 4. That means there have to be 4 zeros. Now, negative 4 is a 0, it says as a 0, but it's a 0 of multiplicity 3. What does that mean? That means it occurs 3 times. And 0 is a 0 of multiplicity 1. Okay, so negative 4 has multiplicity 3. Means this. Z1 equals negative 4. Z2 equals negative 4. Z3 equals negative 4. And the fact that 0 has multiplicity 1 means that Z4, let's put it over here, Z4 is going to be 0. Now, once again, we're assuming that the leading coefficient is 1. So we're going to have f of x equals a times x minus z1 times x minus z2 times x minus z3 times x minus z4, because there are 4 zeros. If you had 5 million zeros, then you'd have to make 5 million factors. That's not fun. No, let's not get that many zeros. F of x equals 1 times x minus negative 4 times x minus negative 4 times x minus negative 4 times x minus 0. Okay. So f of x equals 1 times all this, which will be x plus 4 times x plus 4 times x plus 4 times x. Because what is x minus 0? It's x minus 4. So now I'm going to group these two together and these two together so that I will get x squared plus 4x plus 4x plus 16 times x squared plus 4x. Whew. Okay, so this will be f of x. X squared plus 8x plus 16 in parentheses times x squared plus 4x in parentheses. So we will have x squared times x squared plus 4x plus 8x times x squared plus 4x times 16, plus 16 times x squared plus 4x. Goodness. So this will be f of x equals x to the 4th plus 4x to the 3rd plus 8x to the 3rd plus 32x squared plus 16x squared plus 64x. Almost done. Just have to combine like terms now. So f of x equals x to the 4th plus 4x to the 3rd plus 8x to the 3rd is 12x to the 3rd plus 32x plus x squared plus 16x squared is 48. X squared plus 64x. There's your polynomial built from -4 that has multiplicity 3 and 0 that has multiplicity 1. Okay, let's look at what all we have talked about today. We have talked about how the leading term determines the number of zeros, or correlates with the number of zeros, the maximum number of real zeros, the maximum number of x-intercepts because the real zeros make the x-intercepts, and the maximum number of turning points is always going to be one less than the highest power in the polynomial, which is the degree of the polynomial. And that's always going to be true if you're dealing with polynomials. Then we showed how zeros of all kinds, whether they're real rational, real irrational, or complex conjugate, or just complex, how they build polynomials. They start out as little bitty numbers on the x-axis and boom, they build a whole polynomial. Then finally, we talked about how rational zeros can stand by themselves, but irrational zeros and complex zeros have to have their conjugates with them. No choice. Not if you're going to have real rational coefficients. Okay? You'll learn more about that in calculus. But right now, it's enough just to memorize that you're not going to, that all your problems, okay, all of the polynomials you're going to be building say that you have to have rational coefficients. That means that all of your square root radicals and all of your I terms have to have their conjugates with them, no choice. And these middle problems show you how, when you do have conjugates, how after you work through the whole thing, you do have rational coefficients, real coefficients and rational coefficients. Okay, questions, discussions. Okay. Well then, I mean, gosh, we're going to get out early because I have nothing left to share with you. I do have to share with you that tomorrow, what are we doing tomorrow? I don't know. We'll just have to wait and find out, but we might and probably, oh, we're going to be doing synthetic division. Very important technique to learn for what's coming Monday. So you want to make sure you master all of this. Okay. And if you have any time left over, try looking at dear. I think my cat's trying to catch a bird, so I need to go rescue. So I will see you all tomorrow. Bye-bye.